Hello! Today we're going to have a look at the chain rule, and I'm going to look specifically for use of maths. So if you were doing normal maths, there might be other things which you might be expected to notice, but for use of maths, we're really just looking at nice basic functions. It's very rare that you get anything beyond a linear expression inside a function. So I use the chain rule if I've got a function inside a function. So for example, looking at sine 2x plus pi, I've got one function which is 2x plus pi, and that's inside another function which is sine x. Looking at cos x squared, I've got one function which is cos x, and that's inside another function which is x squared. E to the power 5 minus x, well, I've got one function which is 5 minus x, and that's inside another function which is e to the power. Now, normally these are easy to spot because they've got brackets like the sine and the cos, but you'll notice on the e to the power x, there aren't brackets there. But if I was entering this onto my calculator, especially the graphical calculators, the scientific calculators, it'll normally come up with a box and you just type it into the box. But on a graphical calculator, to get the x to be up there with the power, I would need brackets, and therefore the brackets are there, we just tend not to write them. So you've got to remember to put in your own brackets for that one. And that's true of this one as well, 1 over x squared plus 1. Well, I've got x squared plus 1, and then the other function is the power, and this is actually to the power minus 1. And then my final one is ln 5x minus 6. This one's nice and obvious. 5x minus 6 is one function, and it's inside ln x. Now, when I do the chain rule, I pretend that the inside function is just x, and I differentiate it normally. Now, how the chain rule works is I say I've got f of g of x. And what I'm really doing is I'm making a substitution. Instead of writing g of x, I'm going to write u. I'm going to say y equals f of u, because g of x is just u. And what I'm going to do is I'm going to say dy by dx is equal to dy by du times du by dx. So I differentiate the outside function, I times it by what I get when I differentiate the inside function. So let's have a look at our examples. The first one I'm going to have a look at is y equals sine 2x plus pi. So I'm going to imagine instead of 2x plus pi, it's just x. What happens when I differentiate y equals sine x? Well, I get dy by dx equals sine differentiates to cos. So this is cos. But instead of x, I'm going to write my 2x plus pi. And then I need to multiply that by what I get when I differentiate 2x plus pi, which is just 2. So I can say that this is 2 cos 2x plus pi. My second example, y equals cos of x squared. Well, I'm going to pretend that this is just x squared. What happens when I differentiate x squared? Well, I get dy by dx equals, differentiate cos squared, I times by my power, I take one off my power, but instead of x, what was really there was cos x. So I'm going to write my cos x in. But then because I'm doing the chain rule, I need to times by what I get when I differentiate cos x. When I differentiate cos x, I get minus sine x. So I can write this as minus 2 cos x sine x. This next one, before I start, I need to write it in the form x squared plus 1 to the power minus 1. Now I can see that I've got it in the form something to the power minus 1. I differentiate it, so I times by my power, which gives me minus, and it was minus x squared plus 1. I take 1 off my power, and then I need to do my chain rule bit. I need to times by the bit inside my bracket, so I'm going to times by 2x. And obviously I need my dy by dx to say I've differentiated. Now I can tidy this up and I can write it as minus 2x x squared plus 1 to the minus 2. Y equals ln 5x minus 6. I differentiate. I pretend it was ln x, which I know differentiates to 1 over, but it wasn't ln x, it was ln 5x minus 6. So I write my 5x minus 6 in, and then I times by what I get when I differentiate 5x minus 6, which is just 5. I can tidy this up. I can say it's 5 over 5x minus 6. And the final one, differentiating y equals e to the 5 minus x, I'm going to get dy by dx equals, if I differentiated e to the x, I would just get e to the x, so I'm going to try e to the 5 minus x, putting 5 minus x in wherever there was going to be an x, and then I need to multiply that by what I get when I differentiate 5 minus x, which is minus 1. So I can rewrite this as minus e to the 5 minus x. Right, let's finish off by having a look at an exam question. Now, this is taken from a comprehension paper, because there is calculus in comprehension papers. The bit in the square box is from a preliminary material, because the comprehension paper really does focus on the preliminary material. It says, we can also use differentiation to find on which days of the year key features of the rate of change of daylight hours occurs. For example, in London, the number of daylight hours is given by h equals 12.2 plus 4.2 sine, and then n minus 80 pi over 180. You can see here I've got my brackets, and they've found the second derivative. This allows you to find when the rate of change of daylight hours is either a maximum or a minimum by equating the second derivative. This occurs when sine of that thing equals 0. So they've said this is my second derivative, and we need to have a look at how they got to that. The exam question asked us to use the same techniques, but instead of doing it for London, doing it for Oslo. And you can see we have a slightly different equation. We've got 6.5 here rather than 4.2. So in the actual exam, you had to adjust what we're going to go through now for a different number. But the method should be the same. So I'm going to have a look at what happens when we differentiate this thing. H equals 12.2 plus 4.2 sine n minus 80 pi over 180. The first thing I'm going to do is I'm going to write the bit inside my bracket so that it looks like a polynomial, because I know how to differentiate polynomials and I know how to differentiate trig. So I'm going to say h equals 12.2 plus 4.2 sine. And then to make this look more like a polynomial, I'm going to say pi over 180 n minus 80 pi over 180. Now I can differentiate this, dh by dn, and I can say 12.2, when I differentiate it, it's a constant, so it's going to disappear. 4.2 is a number I'm timesing by, so that's going to stay. I'm going to get sine of something. So I'm going to pretend all of this bit is just an x. What would happen if I differentiate sine x? Well, I get cos x. So I'm going to get cos, and it's not actually x, it's going to be pi over 180 n minus 80 pi over 180. And then because we're using the chain rule, I need to differentiate the bit inside the brackets, which is going to give me pi over 180. So this is my first derivative. I can say dh by dn, just tidy it up a little bit, equals 4.2 pi over 180 cos of my brackets. But if we come back up to the top, we notice that actually we're looking for d squared h by dn squared. We're looking for our second derivative, which we're going to make equal to 0. So I need to differentiate it one more time, and again I'm going to have to use my chain rule, because I still have a function which is cos of x, and then a function within my function. So for my second derivative, 4.2 pi over 180 is just a constant which I'm timesing by, so that stays. Cos differentiates to minus sine, so I need a minus and then sine, and then I'm going to have my brackets in as they were before. But then because I'm using the chain rule, I need to differentiate inside my brackets, which gives me pi over 180. I can tidy this up again, so I can say it's minus 4.2 pi squared over 180 squared sine pi over 180n minus 80 pi over 180. Now, we want to know where the second derivative equals 0, so I'm going to put this equal to 0, and then I'm going to divide both sides by minus 4.2 pi squared over 180 squared to get rid of it. So I get 0 equals sine pi over 180n minus 80 pi over 180, which isn't quite what they had here, because they're factorized inside the brackets. If you remember, we expanded our brackets to make it look nice for me to be able to differentiate. Now I need to factorize my brackets again to finish off. So I'm going to say 0 equals sine. I'm going to factorize out my pi over 180, and that leaves me with n minus 80. And now, if we have a look back at the start in the pre-release, that is what we were after. Sine n minus 80 pi over 180 equals 0, and that's what we've got. So that's how the chain rule works for use of maths.